All right, welcome back to the SciMax channel on Electronic Lab Notebook series. Today I'm introducing another new design of experiment approach called Latin squares or Latin hypercubes, and how we can use that in our notebook and use it to run experiments on instruments and what kind of experiments these are good for. So a Latin square is shown in the figure over here. And it's a way, in this example, we have 3 values of, say, red, 3 values of blue, and 3 values of green, and we want to know, do those have an impact on something that we measure? Now, 3 by 3 by 3 would mean 27 experiments if you tried to do this in a factorial kind of design, and this is a lot. And so what we're going to do here is use a blocked example where there will be 3 examples for each one in an orthogonal kind of way, and then we can do an analysis of variance on the blocks in the measurements to see whether they have an impact or not. There is surprisingly not a good Latin hypercube package in Python. There are things in SciPy that do Latin hypercube sampling, but that's not the same as this. There is a Latin hypercube design in PyDOE3, but it's also not this. And I couldn't find something else and wanted to have this for kind of general capabilities. So let me show you how I have it set up. All right, so this first example is from Statistics for Experimenters, classic statistics textbook. And the problem at hand is we want to test the effect of an additive on car performance. So we have 4 additives to test. The problem is that we also have 4 cars that we want to test it in, and there are 4 drivers that will drive them. And you know, some drivers have a heavy foot, some drivers might drive very conservatively, and that could have an impact on the performance that isn't related to the additive. And if we have different cars, they might be different ages or different models that also could have an effect on performance that isn't due to the additive. Now, we don't want to do 64 experiments to try all 4 combinations 4 by 4 by 4, and so instead we're going to do this Latin square design. And this is only going to take 16 experiments. It's going to be a 4 by 4 array. The rows will be like the cars, the columns will be the driver, and then we'll have the additives set in an orthogonal way in each entry. All right, then the simple idea, this is the most important idea to come away from, I think, with the Latin hypercube, is that we're going to say the result is the overall average plus an effect from factor 1, plus an effect from factor 2, plus an effect from factor 3, and then everything that's left over will be residuals. Now, we can look at the variance, it's like the standard deviation squared of the residuals, and compare it to what we get for these effects, and determine whether these effects are significant compared to random noise that is ideally is left over. Okay, so that's really the idea. It's not a very sophisticated model. It took me a couple of days to work out a full package that I like and can show you sort of the main idea. And I'm going to show you 2 ways to use it today. The first one is in this example here. So this is the setup. This is an sklearn-like library. You'll see what that means mostly when I come to using things like fit and mostly fit. And we just define a Latin square. I use a dictionary right now that allows me to give labels for the factors and the levels. So here we have 3 factors and 4 levels. So 4 cars, 4 drivers, 4 additives. And in the next example, I'll show you we get an actual design, but in this example, there is data from this book, and it looks like this. So this is a straight up regular org mode file, org mode table, and I should probably make a whole video on tables in org mode because they're so helpful. It's plain text, but it's highlighted in green because org mode sees it as a table, and we can use this, I named it results. We can use this as a data source. So I can use this text that you might have typed or imported from somewhere, and we're going to use it in the next next cell. So basically each row here is an experiment. So this is car 1, driver 1, additive A, and the result is 21. I don't remember what the 21 is. It could be like miles per gallon or some emissions. I think it was emissions in the book. It doesn't matter a whole lot. You see some of these are low, like 15 and 17. Some of them are high as 27, 26. So clearly there are some effects due to all of these factors, and the question now is which ones are most important. Okay, so to use this we need a data frame. So I need to convert this table into a data frame, and I do that here by using a variable in this cell block. This is something that's not easy or maybe even possible to do in Jupyter Notebook. Here we're going to make a variable called data that contains the table that is named results above. That's right here. And it's a little unintuitive, but I have to put call names no, which I think means do not remove the column names, which is default. And that's because I want to get those column names as the names of my data frame. So first I make a data frame out of the data, which is coming from this table. I specify the columns to be the first row, and there's an empty row in there that I drop that doesn't have a name, and then we choose the rest of them. And let's see, 0 to 15. The index now goes from 1 to 16, and we now have a data frame that contains all of our data. You can get this from in many, many ways. You could have an Excel file that you read into pandas. You could have a CSV file that you read into pandas. You could type the array by hand and then make the data frame. Lots of options. I like using the tables in org mode because they have a lot of nice features that I should talk about another day. Okay, so once we have that, then we're ready to fit the data. And I use the sklearn-like API here where you give it some X data and Y data. And this is going to be helpful later because we'll be able to have different results, for example, R out, B out, G out, and then do the analysis by just changing a column name here. So when we do this fit, it generates this table down here. So here again, we just have a repeat of the actual experiments and data. This is the average of all of that data. So we start out with an average of 20. And then the cars have different effects. So car 1 will reduce by 1. So that means the output will become 19 if we're driving car 1. Car 2 has no effect. Car 3 has -1. And car 4 is +2. So if we're in car 4, then we have average plus car 4 is going to be 22. And then you see the drivers here. They have different effects. Some drivers make the measurement go up, some make it go down. And then the additive has a similar effect. Some make it go up, some make it go down. And then we have some residuals here that are left basically like plus or minus 1. It's not always this good, as we'll see. But this is the basic fit of the Latin Hypercube. Maybe this is just a Latin square. Hypercube might have a fourth factor that isn't currently supported. All right, now we do the analysis. So here I just run analysis of variance, and what we get out of this is this F-score is a ratio of the variance of the effect to the variance in the residuals. So we get a variance of 1 here. You get a ratio of 5, a ratio of 27, and a ratio of 3. And on this, up here I have a kind of a critical FC score. This is F critical. So any factor that's greater than this is considered significant. And so the residuals are not significant. The car in this example is not considered significant. The driver is very significant. 27 is much bigger than 4.8. And the additive is, it's probably significant. It's just above this, and I should note this significance is at 95% level. So we can look at the drivers and see what the average effects are. So the driver 3 has the most negative effect. They hurt performance the most, and driver 2 has the best effect and makes the performance the highest in general. And it's a little less clear what you can say about the additives. The effects of additives are smaller than the effect of drivers. So maybe this one is the most positive, but you probably want some more experiments with less variation in these other factors to be certain that this is the difference. It could be interesting just to note that driving better is more important than putting an additive in the car. Okay, that's the basic example. Let me show you now how to apply this for the SDL-Light measurement. And so today what we're going to look at here is whether the RGB inputs have an effect on each channel that are measured. All right, so we set R, G, and B, and we measure something close to R out, G out, and B out. And we explored this before. If I look down here, this is how the different channels depend on R, G, and B. And so obviously R depends strongly on varying R, but this slope is not flat. There's a small effect, apparently, on the G and the B. And then if we vary G, G is very sensitive, B is less sensitive, but obviously sensitive, and then R shows a small effect. It's not totally flat. And then similarly with B, you see a huge sensitivity on the B output, some on the G output, and less on the red output. Okay, so this took a lot. Every one of these data points is an experiment. And so we ran, I don't remember how many, probably like 20, looks like about 20 different experiments to do this. And what we'll do today is look at the effect of using a Latin square to answer the question of, is there an effect or not? And maybe how big it is, but not as quantitatively as we have over here on the right. So I'm going to use 3 settings, 25, 50, and 75 for each channel. And we're going to make this into a Latin square. That means instead of doing these 20 experiments, we can actually do, this might actually be 40 experiments or 60 experiments since we did each channel. We're going to do 9 experiments. Okay, so I'm going to run this, and these are the 9 experiments that we're going to run. And I've shuffled these because it's considered good practice to shuffle them and do the experiments in a randomized order. So these are the actual experiments we want to do. There is a pivot table version that shows us the more traditional looking Latin square. So these are the, I believe these are the B settings. These are the red settings, and then these are the green, red, and then these would be the blue settings on the inside. So this is the more typical 3x3 array that we would see. This setup code is old. We've used it lots of times. I'm just reusing it. Probably by now I should have made a Python library so I could just import it over and over. But I have it here, and this is what we use. So we're going to measure the red, the green, and blue, and we'll get an array of 3 results for each measurement. All right, and then down here, I get them here. Those are cached, so this is going to happen really fast. And then I add them to our data frame so that we end up with a data frame that looks like this. These are, each row is an experiment. These are the inputs. These are the measured outputs. And now we're going to pick one of these at a time and do our analysis. So let's start looking at the right. Let's look at R out first. All right, so I'm going to fit the inputs R, G, and B to R out. And it's not very easy to see. Maybe this is easy enough to see on your screen. What we have are the effects and the residuals. So you can see the residuals here are in the range of say 30 or 40 up to 120 in magnitude. This is larger than the uncertainty in our measurements, and so we know that we're not capturing everything with just these 3 variables. And previously we knew that we needed some quadratic terms in there. But if we do our analysis, what we get here is that for the red channel, the red effect is the most important, and these other ones are not important, right? So like statistically speaking, you might argue this is basically flat in the range that we've looked at, or the effect here is not much more important than the residuals, the random noise, right? Even though the ratio is 3 times higher, it is at the 95% confidence interval, not considered relevant here. And that kind of is a reasonable thing to look at here. Let's look at the G out. With G, we expect 2 things to be at least important, and if we look at that, that's what we see. We see the G effect is the most important. That's the closest and the most significant. The B effect is also relevant, like B seems to have an effect on G, and the red doesn't really seem to have any impact on it. And if I look at the B out, then we find similarly that changing B has an effect on these parameters, and this one is the most important in doing that. And these residuals are actually kind of close to the noise level we expect. I've been seeing somewhere in the 10 to 20 range of variation in the past. You can look at the effects here. So, changing R is not a big deal, doesn't have a big effect on it. Changing B has a notable effect, plus or minus like 5,000 from the average, and changing G has a lower effect on this. So what are we looking at? B out. So changing G has an effect of plus or minus 2,000 over this range, which is pretty substantial compared to changing R. Okay, that is all for today. This is a new package new package for doing design of experiments with Latin squares. It's a very simple model that is sometimes helpful and now seems to be practical and possible for at least these simple examples. And the code is still pretty alpha, so I would still expect there to be some changes as we use it and find different things we want to do with it. But otherwise, this feels like a pretty good introduction to Latin Hypercube design of experiments in electronic lab notebook and using the SDL-Light. All right, thanks for coming.